Hello everyone, this is Kowshiq Kattamuri. So in the last class, we actually took some problems, we solved them, and from that part we shall continue now. So in this today's session, we shall actually solve three problems, and then we'll continue to the part of matrices in the linear algebra part. So I'll just give a light introduction about the linear combination of the vectors and how do you represent them um, in the matrix form, and what is the main simplicity, like what's the main benefit that you get from doing it. So that we can actually see today in the today's session. Like there's a small introduction to it. In the next session I'll then continue it with the equations and all the stuff. So right now in today's session we'll limit to that part. So introduction to matrices will be the last like the ending part of our today's session. So let us see this problem. So the question is, I should use a different thing. Okay, this seems to be good. Yeah. So if the magnitude of v vector is 5 and the magnitude of w vector is 3, then what are the smallest and largest possible values of magnitude of v minus w, and what are the smallest and largest values of v dot product of v vector and w vector. So I just want to remind you guys once again, these are all the fundamental parts of linear algebra. Fine. Once we get enough clarity on all these topics, once we feel that we are enough proficient in all these things, then it becomes so easy for us to understand the further more topics. Fine. So don't think like don't be like because these are easy we can just avoid practicing them and all the stuff. No, each and everything is very important. So I want you guys to please concentrate on each and every small stuff, even small theorems or formula, everything matters. Fine. So that's how you build your linear algebra basics, and then you extend your conclusions from 1D 2D to 3D until ND. Fine. So that is the logic behind learning linear algebra. So the very first way to tackle this problem is using triangular inequality, because we are asked to find the value of like smallest and largest values of magnitude of v vector minus w vector. So this is the triangular inequality. Magnitude of v vector minus magnitude of w vector is less than or equal to magnitude of v vector minus w vector is less than or equal to magnitude of v vector plus magnitude of w vector. So that is 5 minus 3 is less than or equal to this, the required part, and is less than or equal to 5 plus 3. So we get 2 is less than or equal to magnitude of v vector minus w vector is less than or equal to 8. Fine. Now the second part. So what are we we found this, now we need to find this. Fine. So for this part, I'm damn sure at least 30 to 40% of the viewers will be confused to move to the next part, like what we actually need to do. It's not like we are not proficient in, it's not like we are not clear with our basics, it's like the immediate logic. Fine. So getting that is tough. Some people, like 30 to 40% of the viewers, because they feel like these are all the basic stuff and they don't concentrate even at the beginning of the sessions. So because of that, they fail to get the answers. So that's the reason I'm asking you people to focus on the basics. Whether if you know them already or not, it doesn't matter, but be focus on the session like as if you are new to it. Then only you can concentrate on each and every part. Fine. So now scaling on both sides, we get yeah, fine, this is better. So 4 is less than or equal to magnitude of v minus w vector whole square is less than or equal to 64, and this can be written as the dot product of v minus w with itself. So we get this part, like 4 is less than or equal to magnitude of v square plus magnitude of w vector square minus 2 times dot vector of v vector and w vector is less than or equal to 64. So we get 4 less than or equal to 34 minus 2 times dot product of v vector and w vector is less than or equal to 64, and from this you can get this. Fine. So don't be confused, because it's minus 30 and 30 here. Even if you subtract divide by minus 1, you get your inequality signs change and you finally end up with the same result. Fine. So don't be confused, because it's 15 and 15 over here and there, like the both sides are the inequality. So people may think that I have written something wrong or something, but it's the same thing. Fine, you don't need to change all the stuff. So yeah, we are done with the very first question. So this is all about it. It's too basic, fine, but it's like we can only guess sense its value once we go to the further sessions, fine. So it's better stick to it, stick to the formula that every basic part is important when you're actually learning linear algebra, fine. So coming to the second question, can three vectors in the xy plane have u dot product u times v, like dot product of u vector and v vector less than 0, v vector and w vector less than 0, and u vector time u vector and w vector less than 0. Find the dot products. So u vector, v vector, w vector, three vectors in the xy plane. So can each of their dot product be less than 0? So let us limit ourselves to r square, like r square plane. So this is the condition, like this is how you need to do it. So you first need to limit yourself to the easy part, like to the 2D part. Right now it's plain right now, so limit yourself to that, and once you get enough conclusions from it, extend that to the n dimensions, fine. That is the logic. So for example, if you consider u vector to be xi cap plus yj cap, and v vector to be ai cap plus pj cap, and w vector to be mi cap plus nj cap. Now u dot product of uv is less than 0 if, when you can just multiply them, you get ax times by is less than 0, dot product. Okay, so v times v dot product of v w vector, we get f is less than 0 if am plus bn less than 0, and u vector times like u vector of and w vector dot product is less than 0 if mx plus ny is less than 0. From this you can say that you can find n number of combinations, isn't it? There is no restriction. You can find n number of lot of combinations. So for example, if I take u vector to be 1 comma 1, v vector can be minus 5 comma 4, w vector can be 1 comma minus 2. So when you do this, u vector dot product of u vector and v vector, dot product of u vector and v vector, we get the result to be minus 1, isn't it, which is less than 0. And v vector and w vector, we get this result to be minus 13, I guess. I think I'm not wrong. Minus 5, minus 8. Okay. And when you do the dot product of these u vector and w vector, you get this result to be minus 1 again. So which is less than 0. So this is how it is. So you get a number of combinations. There is no restrictions for you. So therefore, for r square, like for the 2D plane, we are getting three vectors. Fine. Four vectors you cannot. You cannot have four vectors which have the dot product is less than 0. So another view of thinking this is dot product is less than 0 if the cos theta is greater than the theta part is greater than 90, isn't it? If it's greater than 90, then you'll be ending up with some obtuse angle, and cos of that will result you in negative value. So if that is the case, your u vector dot v vector will be less than 0. And if I take three vectors, fine, this is this is one vector, this is one vector, this is one vector, and this is total angle is 360 degrees, and when you divide that by 3, you get this angle to be 120 degrees, fine. So there are many cases possible in which all the angles between them is greater than 90, isn't it? It must be greater than 90. Like you can say that, for example, if I take an angle here to be 145, then the other two angles that are left, so 360 minus 145, you'll be ending up with 215. Yeah, 215, I guess. So 215, and when you divide that by 2, again you get that to be 107.5, around that. So you may say, like, if you want to make sure you reduce this less than 90 and this to be 90, you'll be getting this value to be greater than 145. Fine. Like there are many cases, and the main part is it's not like it's impossible for you to create such situations. There are many situations in which you can actually have the angles, each and every angle, to be greater than 90. And if it's greater than 90, if theta is greater than 90, then automatically your dot product will be less than 0. So that is the logic. Now if I take four vectors, this vector, this vector, this vector, this vector, and the total angle is 360 again, and when you divide this by 4, you get 90 degrees, fine. So the limiting condition here is 90 degrees. So if I consider one angle to be 105, the other angle to be 96, the other two angles 105, 96 to 105, what we are left with 159. So if I take this to be 86, and the other part gonna be 73. Fine. So these are the angles. So you can see that this product will give you greater than 0 dot product. This will be giving you greater than 0 dot product, and this will give you less than 0 dot product. This will give you less than 0 dot product. But it's not possible. Like if you wanted to increase this angle, if you wanted to increase this angle, even you can maximum increase it to such an extent where you'll be ending up with only three dot products which is less than 0. The fourth one will be equal to 0. It will not be greater than 0 maybe, or it may be greater than or equal to 0. I hope you guys are getting my point. So basically thing is, when your limiting angle is 90 degrees, you can either increase some other angles and decrease some other angle, but you cannot get all the angles to be less than 90. Okay, you cannot get all the angles to be less than 90. So if that is the condition, I mean all the angles to be, like your main condition to be is like this to be less than 0. The dot product should be less than 0, and for that to happen your theta should be greater than 90. So if theta because 360 by 4 which is equal to 90, so that is the limiting condition. So when you're actually dealing with limiting condition, either if you wanted to increase all the angles by 1, okay, 91 degrees, 91 degrees, 91 degrees, 91 degrees, in all the cases you'll get the dot product to be less than 0. But when you add them up, you get this angles to be 364, the total sum, which is not equal to 360. So it's not possible. So even if you try to do something like that, it's not possible. That's what I'm trying to say. So for that, if you're increasing this by 91 angle, you must decrease the other part by like 1, that must be 89. And if you're actually trying to increase this by 1, you must actually decrease this by 2, that should be 88. So if that is the case, this will be greater than 0, the dot product, and these 3 will be less than 0. But you want all the 4 of them, all the 4 dot products to be less than 0, which is not possible. So that is what that's what I'm trying to say. So it's not possible for you to have 4 different vectors to have the dot products, each and every of them dot product to be less than 0. So that's all about it. So therefore for R square, 3 vectors in the plane can have the dot products less than 0. That is, the angle between them is less than 90. But 4 vectors cannot have all the dot products less than 0. That is 360 divided by 4 is equal to 90. So the limiting case here is 90 degrees. Fine. Now extending this conclusion to R par. So we can say that there can be n plus 1 vectors whose dot product is less than 0, because in R square we got 2 plus 1 which is equal to 3 vectors. So in Rn we get this dot products which is less than 0. So the vectors can be n plus 1 vectors. And the other part proof that we can say is the conventional proof. Fine. The vectors from center of a regular simplex in R parent to its n plus 1 vectors all have negative dot products. So what do you mean by simplex? So simplex is the most simple figure that you can draw using n plus 1 vertices in R par n. Like R, if you take R, okay, so then it will be a line. You're using this vertex and this vertex, like line segment. Take a line segment. If it's R square, you can use a triangle, and if it's R cube, you can use you can draw something like this. Which uses 4 vertices. Fine. So this is our vertex. So this is a simplex. Fine. Simplex, the most simple thing that you can actually consider. So it vectors take R square, okay, triangle and R square, that's a plane with coordinates 20 to 20, 25, B 4, 5, C 3, 6 as its centroid, because it's a triangle. So its centroid is defined, so that is 18, 12. You can just do x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3. And now let us form the vectors from the centroid to each and every vertex dA, dB, dC. So dA vector is minus 2i cap minus 13j cap, dB vector is 4i cap plus 7j cap, and dC vector is minus 12i cap plus 6j cap. You have given with all the vertices position vectors, you can just subtract them, you get the vectors. Okay. Now u vector times v, the dot product of u vectors and v vector will give you minus 99, which is less than 0. V vector and w vector, that is minus 6, is less than 0, and w vector and u vector is minus 54, which is less than 0. Therefore 3 vectors, that is 2 plus 1. So in R square we get 3 vectors which have all their dot products to be less than 0. So it's a simplex in a regular simplex, okay, in a regular simplex R parent, to you get all the negative dot products. Fine. From the center to the vertices through n plus 1 vertices, you get all the dot products to be less than 0. So extending this proof to R power n, we get this to be n plus 1 vertices. So that is all about the second problem. So hope you guys understood. So this is an important logic that people need to consider. Like I'm sorry if I'm not able to deliver you properly the concept that is needed, but I request you guys, if it's not clear, just try to watch the video once again so that you people get enough clarity. And that's all about second question. And coming to the third question, pick any numbers that add to x plus y plus z is equal to 0, like any three numbers, so x, y, z, and their sum must actually be equal to 0. Find the angle between your vectors v is equal to x, y, z and the vector w is equal to z, x, y. So these are the circular images. Like if you rotate it, you get z, x, y. So that is equal to, this is equal to w in this case. So consider v vector 1 comma 5 comma minus 6. So because x, y, z must sum up to 0, so 1 plus 5 minus 6 is equal to 0, so I have considered this. Then w will be equal to z coordinate, like we must rotate this in this anti-clockwise fashion. So we get minus 6 comma 1 comma 5. Now cos theta is equal to, you can just have the dot product and divided by each magnitude, each other magnitude, the product of each other magnitude. So that is minus 6 plus 5 minus 30 divided by, because all these three vectors are the same, like give the same magnitude, isn't it? So that is root over 36 plus 25 plus 1, so root 62, and this will actually give you cos theta to be minus 1 by 2, and because this is minus, this means this theta is equal to 120. So on generalization, we can say that if x plus y plus z is equal to 0, then cos theta is equal to minus r, provided the two vectors have been considered as regular circular images of each other. Fine. It's not like if your x plus y plus z is equal to 0, like if you consider this vector and consider some other, the second vector to be a comma b comma c, which has no relevance with v, you'll be getting this cos theta to be minus r. Okay, that's not the case. So you must have the second vector to be the circular image of the very first vector that you have chosen. So the dot product of v, the proof here, so the dot product of v vector and w vector is xz plus xy plus yz, isn't it? So because xi cap plus yj cap plus zk cap is your v vector, and w vector is zi cap plus xj cap plus yk cap. Fine. So when you multiply this, you get xz plus xy and plus zy. Fine, this is what you get. And now when you just divide and multiply by 2, so you get 2 of xy plus yz plus xz divided by 2, and this is basically nothing but I'm using this formula, a plus b plus c whole square is actually equal to a square plus b square plus c square plus 2 times ab plus bc plus ca. So I've used this formula. So instead of 2 times ab plus bc plus ca, I've written this as a plus b plus c whole square minus a square minus b square minus c square divided by 2. And now it's given that x plus y plus z is equal to 0. That is the condition that we have taken. So v times the dot product of v vector and w vector will be equal to minus half of, so this x square plus y square plus z square can be written as root over x square plus y square plus z square into root over x square plus y square plus z square. Fine. And now this is actually the magnitude of v vector. So and this is actually magnitude of w vector, so you can write this, and if that is the case, this can be replaced by cos theta, and cos theta is equal to minus of theta is equal to 120. So this is how you extended your conclusion, like from you generalized it. Fine. So if x plus y plus z is equal to 0 and the two vectors that are given are circular images of each other, then the cos theta will definitely be equal to minus of in every case, in all the dot product cases, and that theta will be equal to 120 degrees. So this is all about the third question. So these are very fundamental, to be honest. Like there's nothing more logic or anything like that you need to invest into it. You just need to go through the formal procedure and get the final answers that are required. So these are all like testing your basic skills. So how far you're good, like how is your command on the subject, how is your command on the basic stuff, that's all being tested here, nothing more else than that. And now we are coming to the part that is matrices. So I didn't write anything here because by teaching while like what something is being taught, it's better we write it simultaneously while teaching, so then it makes sure like everyone is paying enough attention. Fine. So that's the reason I haven't written anything here. So we shall start now. Matrices. Let us consider three vectors. Fine. Let us consider three vectors. U vector to be 1 comma 1 minus 1 0, and v vector to be 0 1 minus 1, and w vector to be 0 0 1. Fine, these are the three vectors that we have taken. Now if I wanted to write a linear combination of this vector, like three vectors, let us assume that as to b vector. Fine, if I wanted to write the linear combination of these vectors, I can write this as x1 u vector plus x2 times v vector plus x3 times z vector, w vector. Fine, so this is the linear combination. So that means this is x1 times 1 minus 1 0 plus x2 times 0 1 minus 1 and x3 times 0 0 1. Fine, and you get this to be x1, and this you get to be x2 minus x1, and this is as x3 minus x2. Fine, so this is the b vector, isn't it? So this is how you get it. Now this is the linear combination. Fine, linear combination of the u vector, v vector, w vector. You are getting another vector, that is b vector, that is x1 x2 minus x1 x3 minus x2. Now how do you represent this? How do you represent this in terms of matrices? Fine, so it is like the multiplication of matrices. Fine, multiplication of matrices. So how do you do it? So what are the different matrices that you can consider here? The very first thing is, here the numbers x1 x2 x3 are being multiplied with the vectors u vector, v vector and w vector. So we shall now use these things, like use the things that are given, use the stuff that is given. Like you have given with u vector, we have been given with the v vector, we have been given with w vector. So we shall use these things to actually represent this this linear combination in terms of the matrix. Like we are representing this in terms of matrix multiplication. Fine, the combination of columns, you can say that. So first of all, let us combine these three. Okay, so when you do it, you get 1 minus 1 0 0 1 minus 1, and you get this to be 0 0 1. Fine, this is what you get. And now this is a 3 by 3 matrix, and for this to be multiplied, you need to have some other matrix which has 3 here with in the row position. So and now you can have this to be like the resulting vector is a b vector which has only one column, so this can be 1. And what this should be x1 x2 x3. I hope you guys got my point. So I'm actually using all these things just to make sure you understand what I'm actually doing it. It's not even necessary to do all these things. You can directly write the stuff. You can directly write the matrix multiplication in this way, just to make sure we get our basics right, we don't end up in confusion and all the stuff. I'm taking all these things. So it is 3 by 3 matrix, and for that to be multiplied for the multiplication to work out, so we need to have this the other matrix to be in the form 3 is to some other number, and for that the other number can be decided, because here the linear combination, the result of the linear combination has only one column, so it is 1. And also it's an of course obvious thing that it must be x1 x2 x3 itself, and for that the column will be only 1, and this will actually result into the value x1 x2 minus x1 x3 minus x2, and this is actually nothing but the b vector. Fine, so this is how it is. So you are actually multiplying this a vector, you are acting a vector on this part, and this you can consider as another vector. The components x1 x2 x3 are the components of an x vector. You can even take this in this, like you can even consider this in this way. So you are acting a vector upon x vector to get something like b vector. So this is how the linear combination can be represented. Like this is how it is represented. So you are multiplying them and you are finally getting an answer. So this is how it is. So initially you are multiplying the vectors with the numbers. Now you are multiplying with a vector. Fine, now we are multiplying it with a with a matrix. You are multiplying it with a matrix, that is a vector. So that is the matrix A. Okay, I shall write this. Green looks good. So the matrix A acts on the vector x. So vector x has the components as x1 x2 and x3. Fine, these are like this is how it is. So ax, so this can be written as ax is the combination of columns of A. So so yeah, so ax, yeah, just a small adjustment in the screen. Fine, it looks good now. Okay, Yeah, so it says the combination of your like ax, you're actually combining them, you're actually linear combination, it's a linear combination of the columns of a, that is the components of a, that's u vector, v vector and w vector, and you're getting another vector that is b. So this is how you write it. And now we can even consider this as the another components, like x1 to be b1, this to be b2, this to be b3. So this is another component, like this you are representing in the component system. That's it, there's nothing different. So this is how it is. And now just to make show you guys some interesting fact, nothing else, we are actually concluding our session now. So this a vector, so I can write this using, yeah, pink looks good. So a vector is can be termed as difference matrix. Fine. So why am I terming it as in that fashion? Because you can see here, when you're actually acting matrix A on the vector x, its components are getting subtracted with each other. So x1, this difference can be written as x1 minus 0. Fine. So you can usually assume x0 to be x0. Fine. X1 minus x0, x2 minus x1, x3 minus x2. Right. You are getting your components, you are getting the result as the subtraction of the components of the vector x when you are acting a upon it. So for example, if I consider the x vector to be 1 7 9. Fine. If I consider the x vector to be this, and when you apply this a vector on here, you're getting the b vector. Fine. You don't even need to do all these things. It's a direct application, isn't it? So you get 1 7 minus 1 6 9 minus 7 2. Fine. This is what you get. So actually getting your components of x vector being subtracted, and that you're giving the output. That you're giving the output, like your output is actually the difference of the components of the vector x. So that is being happening because of you're applying a on it. So you're applying a vector onto it. So that is the reason a is known as the difference matrix. You can even extend this. Fine. Now you're trying to implicate your logics onto the other dimensions. Now you can actually extend it, because this is a 3 by 3 matrix. What if you're doing for a 4 by 4 matrix? Fine. You can actually write this as, so I'll just take the reference from here and I'll be using white ink. So you can write this to be 1 0 0 0, and this minus 1 1 0 0, and this to be 0 minus 1 1 0, and this to be 0 0 minus 1 1. I hope it works. Fine. And now you are given with some vectors x1 x2 x3 x4, and you can actually try it out once. So you get the result to be x1, and you get x2 minus x1, and you get x3 minus x2. Am I right? Yeah. And you get, yeah, of course it is. There's nothing wrong about it. So this is what. So you are extending it. So for finding the output matrix of the differences, you're just applying the your, what do you say, the multiplication. You're applying the you're acting a onto it. So for example, if I give you the same question in this fashion, x1 the linear combination, if I want you to give me the output b as the difference of components of x vector, then it would be it would have been a difficult task for you to do it. Rather, when you actually apply that like when you change the representation, like fine, when you're actually doing it in the terms of the matrices, you are actually ending up with a very soothing result. Like it's a very easy doing it. You're just extending your conclusions from 3D to 4D. Fine, this is how you do it. So like you have extended this part. This is 0 minus 1 1 to 0 0 minus 1 1, and from there you are actually getting the required output. So this is again the differences. So these are again differences, and this is known as the difference matrix. So, and also I'm hoping that the matrix multiplication is clear to all of you, like the row time multiplication of a row at a time. So one is being multiplied, this row is being multiplied by whole of the stuff, this row is multiplying by all of this stuff once again, this row is being multiplied by this stuff again, this row again is again multiplying this. Fine, this is the pattern. Fine, this is a pattern, and you're getting the output. So I hope it's clear. If it's not clear, then I'm not at all expecting you people to be proficient enough in linear algebra. I want you guys to build your basics. So I'm definitely expecting, I don't even expect 1% of the viewers to be in that stage. So that's all for it. All about it today, and The very best part that I wanted to take is in the like I've cleared the other stuff, the problem stuff. That's very second problem, the logic that I've explained you, that simplex stuff and all these things. These are all very basic part. So once you get enough knowledge about all those things, it will be very easy for you to tackle many further problems in the upcoming sections. Fine. So I hope you guys got enough clarity and enough understanding upon the subject. So these are all the basic parts. These are the multiplication, representation of linear combination. All these are very basic parts. The next session we'll be continuing with the linear equations and all this stuff, and we'll be extending into the inverse matrix stuff, and maybe and then we can even see independence and dependence vectors and all this stuff, okay, in the next sessions. So yeah, that's all for it today, and thank you for watching us. Stay tuned.